Welcome back to Math with ACE. We're working on statistics with ACE, and we're focusing on checking conditions to perform inference for confidence intervals for a single parameter. So we're going to be dealing with proportions and means and determining what type of problem it is and checking the appropriate conditions. So in a previous video, we talked about the fact that you need to be checking whether the distribution or whether the sample is normally sampled, whether the sample was small in relation to the population to check for independence, and whether you can perform normal calculations. And depending on whether you're dealing with proportions as the parameter, the population proportion or the population mean, that's going to tell us how we check that normal condition. So let's get into it. Suppose that a market research firm is hired to estimate the percent of adults living in a large city who have smartphones. 500 randomly selected adult residents in a city are surveyed to determine whether they have smartphones. Of the 500 people surveyed, 421 responded yes, they have smartphones. Using a 95% confidence interval, compute a confidence interval estimate for the true proportion of adult residents of this city who have smartphones. So I've highlighted information here that I think is important. As we're checking random, independent, and normal, I need to be looking for key pieces of information. What type of problem is this? Is this problem about averages, or is it about percents? Is it means or proportions? In the problem, I am given that I want to estimate the true proportion. So right there, I need to be dealing with proportions, and I'm dealing then with N and P hat. So proportions, this is a problem about proportions. And because it is about proportions, I should probably establish what N is and what P hat is. And P hat is the sample proportion, which tells us how many successes there are out of the sample size. There were 500 randomly selected adults. So N is 500. That means that this is 500 here. And then of the 500, 421 responded yes. That's my success. Yes, they have a smartphone. Success is have a smartphone. Failure is not have a smartphone. So this is binary. I have my sample proportion here. I have my sample size, and now I want to check my conditions. R stands for random. In the problem, was I told somewhere that this sample was randomly selected? I was. I was told here that they were randomly selected. So the sample was stated to be randomly selected. I stands for independence. We want our sample size to be less than 10% of the population size. Nowhere in this problem was I told the size of the population. I was told that I had 500 residents, so N is 500, so I had 500, and I need 500 to be less than 10% of some population. So the way that you check this is, what is 500 times 10? Because if 500 is 10%, then what number is 100%? So you can say 500 times 10 is 5,000, and then you ask yourself, is your population at least 5,000? So let's go back to the problem. Suppose that a market research firm is hired to estimate the percent of adults living in a large city. A large city. Is there going to be more than 5,000 people in a large city? Absolutely. 5,000 is very small if it's talking about a large city. So we can say that it is safe to assume that there are at least 5,000 adults in this large city. And then N stands for normal. Can we calculate and use a z-score, or can we use a z-critical value because the distribution follows that bell curve that's a normal curve? Well, if you're talking about proportions, not means, proportions has p-hat, which means I need to be checking successes and failures. That means n p-hat has to be at least 10 and n1 minus p-hat has to be at least 10. I know that n is 500. And I also know that p-hat is 421 out of 500. We are told without the decimal, the multiplication is really important when you have a decimal, but we're told that 421 were successes. And that's, if you multiply those, 500 and 500 cancel. So 421 is at least 10. What is the complement of that? I could say 500 times 1 minus 421 over 500, and then find a common denominator, which is 500, do the subtraction, then multiply and cancel it out. But if your sample is 500 and 421 are successes, the rest are failures. So 500 minus 421 is going to give me 79. 79 is at least 10. So both successes and failures are at least 10. So what does that mean? It means that our conditions are met, and then we can perform inference appropriately. We can generalize to the population, we can use those values from a normal distribution, and we are not over or underrepresenting with too much bias, and we have independence. And so we can generalize with this information. Let's do another problem. Okay. For this question, I have the Stapplet shown on the right because I know that we're going to use it. It's a little foreshadowing for me. We've seen this problem previously. So just want to know that we've done the calculations for this confidence interval, but we didn't check the conditions. And actually, we should have checked the conditions before we even ran the numbers. The Human Toxome Project is working to understand the scope of industrial pollution in the human body, and industrial chemicals may enter the body through pollution or as ingredients in consumer products. I have not given anything about averages or percents here, I'm not given anything about random. I don't really know much right now. The scientists at HTP tested cord blood samples for 20 newborn infants, so I have 20 in the US. The cord blood of the in utero newborn group was tested for 430 chemicals, pollutants, and other chemicals, including chemicals linked to brain and nervous system toxicity, immune system toxicity, and reproductive toxicity and fertility problems. There are health concerns about the effects of some chemicals on the brain and the nervous system. The table below shows how many of the chemicals are found in each of the infants' cords. Use the sample data, construct a 90% confidence interval for the mean number of targeted chemicals to be found in an infant's blood. Okay, so this says mean. To me, this is mean, which means I'm going to use the mean conditions. Is it random? Nowhere in here do I see some highlighted word that says random. So I don't know that it's random. In this situation, I mean, in a perfect world for our class, we could say we are assuming the sample is random, but I don't know that. This is not stated. We should proceed with caution then, because if it's not stated, how are we supposed to generalize to the population? Maybe these are people that are more prone to being around pollution. I don't know. It's very interesting. Independence. For independence, we need our sample size to be less than 10% of the population. So we have 20 newborn infants, and we're talking about infants in the US. So remember the trick, we take 20 times 10, which is 200. Do you think that there's 200 infants in the US? Absolutely. So 20 is less than 10% of all US infants. We're good to go there. What about normal? For means, we have 3 ways that we can check normal. 1, we are told that the population is normal. This problem doesn't say that. Okay, let's move on to the next one. The next one, n has to be at least 30. 20 is not at least 30. So we have to move on to the next one. We need to graph this and make sure there's no strong skewness or outliers. So in Stapplet, I'm going to go ahead and go to one quantitative variable single group. And I'm going to, let's call it infant blood, enter the data. And now we're going to graph it. I mean, the dot plot doesn't look like something's clumped all to one side, maybe a little bit more to the right. Let's look at a box plot. Okay, maybe there's a little bit of skewness. Don't see any outliers. What about a histogram? I don't love this. I mean, there's no strong skewness maybe, but there's still a little bit of skewness. I don't think it's great. What about a normal probability plot? When you're looking at a normal probability plot, what you're looking for is you're looking for it to be straight with the line and follow that. And it does pretty much do that. So I think we would be safe to say that there's not strong skewness or outliers. So we're okay to proceed. For this problem, I don't love that it wasn't randomly stated. I don't love that there's a little bit of skewness in the plot, but I mean, it's the best we could do, right? Let's do one more. Suppose you do a study of acupuncture to determine how effective it is in relieving pain. You measure sensory rates for 15 subjects with the results given. Use the sample data to construct a 95% confidence interval for the mean sensory rate for the population, assumed normal from which you took the data. Okay. Random. Same issue. This problem does not say that these people were randomly selected. We weren't given randomly assigned any of that. So this problem does not mention randomness. So what does that mean? We really shouldn't be generalizing this to the population if it's not random, because there are many things that could be issues. What about independence? Well, we want N to be less than 10% of the population. So is 15, what's 15 times 10? That's 150. 15 subjects where? Where are these people coming from? The people that get acupuncture? Are there at least 150 people that get acupuncture? I don't know. Is it a small town? Where are these people coming from? We are assuming this. Who are we going to generalize it to? I feel like this is bad data. What about normal? Assumed normal. Now you've encountered a couple of questions. One is regarding proportions, a couple regarding means. Means can be, you can check the normal condition in 3 different ways, but you're really looking for those key words, those key pieces of information to make sure that your conditions are checked so that you can, in fact, perform inference and generalize the information to the population. Let's move on to performing some confidence intervals for proportions in our next set of videos. Thanks for watching, everybody.